Today we are going to take a look at what is called a traveling salesman problem, or the abbreviation TSP. So here we have a diagram. Willie is a traveling salesman and has customers in 5 cities, A, B, C, D, and E. He needs to schedule a sales trip that will start and end at A and goes through each of the other 4 cities. The graph shows the cost of a one-way airline ticket between each pair of cities. What is the optimal, in this case optimal means cheapest, Hamilton circuit for this graph? So we've got Willie here who's trying to plan his business trip. Now we have 5 vertices here, and if you look carefully, we have researched flights between every pair of cities. So this is technically the graph of K5, the complete graph on 5 vertices. Now, anytime you have a graph whose edges have numbers attached to them, we call this a weighted graph. And the numbers are called the weights. So this graph happens to be a complete weighted graph, which in this case is K5. So we are trying to find the best route, which in this case is a Hamilton circuit, for this graph. We want to find the cheapest Hamilton circuit. So there are several methods to do this. We're going to look at 2 today. Now, there is only one way to guarantee that you have the cheapest route, and that is using brute force. You need to list all possible Hamilton circuits, find the weight of each circuit, and then choose the cheapest one. Well, we learned in the last video that a complete graph with 5 vertices will have 5 minus 1 factorial, so 4 factorial, which is 24 distinct Hamilton circuits. So we have 24 different routes to test. Again, as we looked at in the last video, when you are trying to list out all of the distinct Hamilton circuits, the easiest way to do that is to pick a starting vertex. In this case, we are going to start and end at vertex A because that's where Willie the traveling salesman lives. He needs to start and end his route at home. So we have 24 Hamilton circuits that we can list out that start at A. But if you remember from the last video, these Hamilton circuits come in pairs. You have a Hamilton circuit, for example, A, B, C, D, E, A, and its mirror image, A, E, D, C, B, A. So we really have 12 pairs of Hamilton circuits to evaluate. Now, I have already created a list for you. So you can see I've paired up these Hamilton circuits. So we have A, B, C, D, E, A, and its mirror image, A, E, D, C, B, A. And each of these are paired up going down this list here. Now, to calculate the total cost for the circuit, I'm going to look specifically at this first row. So let me go back to the diagram of Willie. So if he goes A, B, C, D, E, A, we're trying to figure out how much would all of those flights cost? So we can do 185 plus 121 plus 174 plus 199 plus 133. Add all of those up and we get $812 for those 5 flights. So that's how I got this cost here. Now, ultimately, we want to know what is the cheapest route. So if you look through this list, the cheapest route is row 11 here at $676. You could either go A, D, B, C, E, A, or its mirror image, A, E, C, B, D, A. But that is going to be the cheapest route. So, if this method always gives us the best answer, why do we need any other methods? Well, this example only had 5 vertices, and we had 24 different options, well, 12 pairs of options to test. As the graphs get larger, you get an insane number of possible distinct Hamilton circuits in the graph. So as you get larger and larger graphs, it gets unmanageable to try to run all of the possibilities. You would need a very powerful computer to help you with this. So it's not the best for larger scale situations, and most real-world applications of graph theory have hundreds or thousands of vertices. So we have a few algorithms that don't always get you the best, but they usually get you a pretty good route. So let's take a look at the first one, which is the nearest neighbor algorithm. So first, you have to pick a starting vertex. If it doesn't specifically tell you where to start, then just pick any vertex. Then you want to go to the nearest neighbor. So the vertex for which the edge has the smallest weight. Then from that vertex, you choose the nearest neighbor that you have not yet visited. If there's a tie, you select randomly, and you continue. And then once you've gotten to the last vertex, you return to your starting vertex. So let's run through this with Willie and see what happens. So we know that he is supposed to start at vertex A, because that's where he lives. So we want to look and see which vertex would be the cheapest. We could go to B for $185, C for $119, D for $152, or E for $133. Well, this one's the cheapest, so that's where we're going. So once we're at C, we want to see what vertex is cheapest. We can go to B for $121, D for $174, or E for $120. Well, $120 is the cheapest, so that's where we're going. Now, we still have to go to either B or D. So from E, B would be $200, or D would be $199. So let's go with $199. All right, so then our only option is to go to B from here, and then from B to go back to our starting point of A. So we started at A, we paid $119 for the flight to C, $120 for the flight to E, $199 for the flight to D, $150 for the flight to B, and $185 back to our starting vertex, which gives us $773. Well, we already have a list of all possible solutions, and that was not the best one. So Why are we going to use this algorithm if it doesn't give us the best answer? Well, it's efficient. When you add a vertex or when you move to a bigger graph, it does not drastically increase the amount of work or the amount of time required. But it does not necessarily give us the optimal circuit, optimal in this case being cheapest. So let's look at a couple vocab words before we're done for today. An optimal algorithm is a process that always gives you the optimal or the best, in this case, cheapest, solution. An inefficient algorithm is one that is going to take a lot of steps to carry out, and as you increase the number of vertices, it gets way more time consuming. An efficient algorithm is one where the amount of time and effort does not get, crazy as you increase the size of the problem. So, brute force is an optimal algorithm. It always gives you the best solution. But it is inefficient. If Willie had more cities to visit, it would take us a lot more time and effort to figure out the best route. Nearest neighbor is efficient. It would be a pretty easy procedure to carry out, even if we had hundreds of cities for Willie to visit. Well, is there an algorithm that is both optimal and efficient? No, at least not that we know of. So we have to make the decision between, is the extra effort to use the brute force method worth it for what might only be a tiny bit better solution? That is it for today. We will talk about a few more methods in the next video.